Okay, I wanted to thank Kirk for recommending this book and to me and suggesting that I speak about it. I had not read this book before, and it was really interesting to learn this field, which is mostly cosmology. Jack Schlachter and I and others were talking about what would the 6 numbers be, and a lot of us thought it would be like the speed of light and pi and the mass of the proton or something, but it isn't about any of those numbers. It's about the formation of the universe and how if these numbers were a little bit different, we would not be here today. So hopefully I can explain this subject. Okay, so I'm going to start. This is an outline of my talk. I'm going to start by telling you a little bit about the author, Lord Martin Rees. Then I'm going to go through the 6 numbers that he discusses and defines and why the universe is finely tuned. And then I'm going to bring up at the end the multiverse hypothesis. And this is kind of in preparation for next week's Faith and Science Forum, where we're going to have Deborah Harzma giving a video presentation, and then she will be available on Zoom to answer questions. And her talk is going to be God and the Multiverse. I have not looked at her presentation because I didn't want to be biased by anything she said. I still don't have a formed opinion about whether I think this multiverse idea is a good idea or not. And scientists are split about 50-50 on whether they think it's the right answer for why our universe is the way it is. And finally, if we have some time, and actually sprinkled along in the book, in the talk, I will talk about advances during the 26 years since this book was first published. A lot has happened in science since this book was first written. And I have many questions at the end, and I hope we'll have some time for a table discussion where you can talk with each other about your questions as well. So first, about Lord Martin Rees. The day I made this slide, he turned 84 years old. On 23rd of June, 1942, he was born. He was born in the UK. He's a cosmologist and astrophysicist. He was the 15th Astronomer Royal from 1995 to 2025. This is a title in the UK. He got his Ph.D. in 1967 at Cambridge, and he was the Master of Trinity College in Cambridge from 2004 to 2012. In 2011, he won the Templeton Prize. Have any of you heard of this prize before? Yeah, a few of you have. Yeah, it's a prize given by a kind of a rich person who started it, and it was for people that were kind of at the intersection of science and religion. And it was a little bit controversial that Martin Rees got this award because he doesn't claim to be religious. He says he doesn't have any religious views, but he certainly isn't an enemy of religion. He doesn't campaign against religion, and he actually participates, as you will see later. He had a couple of causes that he took up later in his life. He co-founded the Center for the Study of Existential Risk in 2012, and this is looking at things that could do in humanity. And artificial intelligence is one of those things that is kind of made the list lately. He also is chairing an advisory board for Breakthrough Listen Project. And this is kind of a SETI project looking for extraterrestrial civilizations. So they're doing things a little bit complementary to the SETI project in the United States. So this is one of my slides, probably the only one I'll have on religion. When he won this Templeton Prize, he was interviewed by The Guardian, and he also gave a speech at the beginning accepting the prize. So these are quotes from that day when he accepted the prize. He says, "I grew up in the traditions of the Anglican Church, and those are the customs of my tribe. I am privileged to be embedded in all its wonderful aesthetic and musical traditions, and I want to do all I can to preserve and strengthen them." So he would feel very comfortable at Trinity on the Hill here today. And he also says, I think doing science makes me realize that even the simplest things are pretty hard to understand. And that makes me suspicious of people who believe they've got anything more than an incomplete and metaphorical understanding of any deep aspect of reality. And I also see that human beings are not the culmination, but only a stage in the marvelous unfolding of evolution, because the timeline ahead is as long as the time that has elapsed up to now. Those are respects in which my professional interests affect my response to dogmatic religion. Okay, so now I'm going to present the 6 numbers. So one of the premises or assumptions in this book is that the laws of physics are the same everywhere in our universe. You can't just go to another galaxy and say, well, gravity must be different there. And we don't have any evidence to the contrary of this premise or assumption. Another point that Martin Rees makes is that it's best to work in ratios or dimensionless numbers because they are absolute and they could be communicated apart from conventions. So if we could define some ratios that were universal across all the planets, all the galaxies, we could communicate those numbers to other civilizations and they would know what we were talking about. For example, the proton to electron mass ratio is 1,836. Now, we don't know what the unit system is or the numbering system of another civilization, but if we could figure out what numbers are, we could communicate all those science quantities, all those ratios across civilizations and start to establish a common language and framework. So the first number he mentions, which probably is maybe the most intuitive of these, is this number n, and it has the value, at least for 2 protons, of 10 to the 36 power. So this is 1 with 36 zeros after it. And it's the ratio of the electrostatic force to the gravitational force. And for 2 protons, the exact number there is, well, to 3 digits anyway, is 1.24 times 10 to the 36. So the 2 protons are both electrostatic and gravitational forces are inverse square laws. They drop off as you move the bodies further apart by 1 over the distance apart squared. But the difference between them is that gravity is always attractive. Any 2 bodies with mass always attract each other, whereas electrostatic forces come in opposite signs. The protons have a positive charge by convention, and the electrons have an equal opposite negative charge. And so they attract each other like this picture is showing. And of course, 2 electrons would repel each other, 2 protons would attract each other. So this is good because the electrons can stay in orbit around atoms, around protons. So gravity is really exceedingly weak compared to the electrostatic force. The only reason we feel that it is a strong force is because the Earth is very massive and we're all very close to the Earth, or right on the surface of the Earth. And the other reason is because electrostatic forces generally cancel each other out. The positive and negative electrons balance each other, given that there are the same number of protons and electrons in an atom. So we feel like gravity is stronger, but really electrostatic forces are stronger. So here's maybe an analogy to this. Here's a picture on the left of the moon. It is quite massive, not as massive as the Earth, obviously, but it's quite big. And because it's got a lot of mass, gravity can pull it all into pretty much a sphere. There's a few mountains on the surface that can hold up, but really it managed to pull itself into a spherical shape. Whereas all of the asteroids, and on the left you can see 2 bodies that are around Mars that are captured and are considered moons of Mars, Phobos and Deimos. See, they all look like potatoes. They're all very irregular shaped and they don't have enough self-gravity to pull themselves into a shape. So it gives you an idea of how weak gravity really is. So Martin Rees makes the point in each of these numbers of trying to figure out what would happen if gravity, if this number were smaller or weaker. And in this case, he gives an example of what if gravity were electrostatic to gravitational force was 1,000,000 times weaker, or gravity was 1,000,000 times stronger. So that number would become 10 to the 30 instead of 10 to the 36. Well, what would happen if it was stronger is that the stars would be smaller. There would be 1,000,000,000 times fewer atoms per star. We would run out of fuel in 10,000 years on a typical star instead of 10 billion years. This is if gravity were stronger, yeah, instead of 10 billion years. And there wouldn't be enough time for life to form on planets around those stars. You know, we've been here 4.5 billion years, and we think Earth, life started forming billions of years ago. So if you don't have a billion or billion and a half years, that's what I learned in last year's book, for life to form, you wouldn't be able to get the complex life we see today. Also, if gravity were stronger, only animals the size of insects could withstand the strong gravity. So we wouldn't be able to get large, tall structures like we are today. And also the galaxies would form earlier. The stars would be more densely packed together, and closer encounters between the planets and between the stars would be frequent, and planets would be disrupted out of their orbits. So all of that would be bad if gravity were 1,000,000 times stronger. On the other hand, this one doesn't seem that finely tuned to me. What if gravity were weaker? Well, the opposite things would happen. It might actually even allow more time for complex life to form. You don't want to get too much weaker, but maybe 1,000 times weaker, you could probably lengthen the age of the universe up more billions and billions of years and give life time to evolve to something more complex. So now I'm going to move to the second number. The second number is characterized by this Greek small letter epsilon here. So that's this right here. You can see the Greek letter epsilon. And epsilon is the fraction of the mass of 4 protons that are converted to energy when they get fused together into helium. Okay, so it's something that talks about the strong nuclear force and how all of the elements are built up from hydrogen and become successively heavier and heavier elements. And you probably all have heard of the E equal mc squared, Einstein's equation. So that shows you how much energy you get by converting some mass m from mass right into energy. So the way we get energy in our universe is we turn 4 protons into a helium atom, and the mass difference between them is converted to energy, to heat, to light, and that's what fuels the stars. There are some later stages of fusion in stars after they're done burning hydrogen. They start burning helium if they're massive enough. Our sun will do that. They're even more massive. They can burn carbon and get up all the way up to iron, even become a supernova. But those extra stages only account for another 0.001 fractional mass conversion. So most of it is the hydrogen to helium. So what I want to show you here that Rees doesn't go into very much is that it is not that easy to turn 4 hydrogens into a helium. It takes a bunch of steps. So in our sun, we have all this hydrogen in the core, and it's 15 million degrees Kelvin. And the first thing that has to happen is 2 hydrogen atoms, these are these protons, these red ones, have to get together. Remember, they're positively charged. They don't really want to get together. Plus, it takes the weak nuclear force to convert one of them into a neutron to stick it to the proton to make heavy water or deuterium. Okay, and you see that 10 to the 9th years, it happens so rarely that it takes 1 billion years for any 2 of these to get together. And that's probably a good thing, because our sun, if it took less time, our sun would burn out right away. It would use it all up, in a few thousand years, and it would be over. So the fact that this is so hard to do is keeping our stars going for a long time. So then you don't just make a deuterium, you have to get a hydrogen again and make a helium-3, and then you have to find another helium-3 for that to get together to make a helium-4, and then it also puts back out 2 hydrogens that can go back into the pool. So this is not a trivial process to do, to make 4 hydrogens into helium. But it was easier in the Big Bang. Otherwise, we wouldn't be here. So in the Big Bang, at the very beginning, in the first few minutes after the Big Bang happened and the universe was formed and started expanding, deuterium was made, helium was made, and a trace of lithium and beryllium were also made. And that's because there were neutrons available in the Big Bang. To right away, you didn't have to use the weak nuclear force. There were just neutrons floating around. I think 15% of the neutrons and protons, there was a proton overabundance, but about 15% of those were neutrons. They were just around, and the mean neutron lifetime is 15 minutes. So they would all decay in 15 minutes, but in the first few minutes, there were enough around to make deuterium. So what you get is you get your proton or your hydrogen, gets a neutron, makes a deuterium, and it can a couple of different ways make a helium-3, or it can make a tritium, and then it can take another deuterium and make a helium-4. So by the end of the Big Bang, after a few minutes, 24% of the mass of the universe was helium. Okay, and that's because we had neutrons. Otherwise, we would not be able to do that. Okay, so what would happen if the strong nuclear force were just a little bit weaker? Instead of 0.007, what if it were 0.006? Well, the problem then for nuclear physics is not good. The proton wouldn't stick to the neutron to make deuterium, so you couldn't make any helium at all, not in our stars. You could still make stars, they would all be out of hydrogen, but they couldn't start the nuclear reaction process, and they would cool off and die after about 10 million years. Our sun would be cooled off and dead. So that wouldn't work for life to form. And what if the strong nuclear force was just a little bit stronger, 0.008 instead of 0.007, like it is? Well, then in the Big Bang, the 2 protons would just bind together quickly, and they would have all combined into helium. You would actually get this nucleus, which is 2 protons instead of just a proton and a neutron, and you would get no hydrogen left to fuel the stars. All of our stars would just be helium. So that wouldn't work either. So this is a very finely tuned number. Okay, now I'm going to go on to the third number. This is the number omega. It's a capital Greek letter, and it is the ratio between the matter density of the universe and the critical density needed for a flat universe. And this is what we think we have, a flat universe that's neither going to expand indefinitely nor going to collapse on itself. Actually, it is going to expand indefinitely, but omega is because we have dark energy, which is coming later. Or that's the next number. But omega would be for a flat universe if you had just enough matter so it wouldn't expand forever and it wouldn't collapse on itself. And we used to think that we should be able to find enough matter to close the universe and make it a flat universe. But we've only been able to find about 30% of the matter needed to make omega equal 1 to close the universe. Whoops. I'm sorry, something happened. And we think that only 5% of that is the normal matter in our galaxy that we can detect through light and heat, infrared radiation. We only find about 5% of it is normal. And the rest of it we have to infer is there by the motion of stars around the galaxies. They're going around too fast for the amount of matter that we see. So we postulate that that must be dark matter. But we don't even know what the dark matter is. We're still trying to find out years later. Now, the rest of this has to be made up by something else. And we've recently postulated and also have some evidence for it that the rest is dark energy. And I'm giving you all these numbers to 3 significant figures. Martin Rees didn't know those to that many significant figures when he wrote the book 26 years ago. He said kind of about 30% and about 70%. But now we have those numbers refined pretty well. So I just want to give you an example of velocities going around something. This is the Earth. None of this is to scale, but here's the Earth, and here's a satellite going around in near Earth orbit, and its velocity is 7 kilometers per second. Now, if you want to keep the satellites out in geosynchronous orbit going around the Earth, they only have to go 3 kilometers per second. And that's because they're further away, so the gravity is not as strong. So they can stay in orbit by not having to go quite as fast. So they're going 3 and the other one is going 8. Now, this next one is showing you kind of a picture of the velocity of objects around the center of our galaxy. Here's the sun, and the distance from the galactic center. Well, if we just looked at the normal matter we have in our galaxy, we should see the velocity, just like that outer geosynchronous satellite, we should see the velocity dropping off pretty quickly here. But instead, we don't see that. We see all these objects that are farther out in our galaxy are going around faster, as if there was more matter inside that they had to stay away from in order to stay in orbit. So we infer from this the rest of the dark matter that must exist that gets us up to our 0.3, whatever that number was, 0.317. 0.268 is dark matter. So you can look at other galaxies and see the same kind of curve where there's all this missing matter. It's still not enough to make it flat. Okay, now I'm going to try to explain what flat means. This is not comprehensive here because there's a lot more. I get another half-hour lecture. But if omega is 1, that's our flat universe here. And you can kind of think of it this way. If you draw a triangle on it, on space-time, all the angles should add up to 180 degrees, just like in geometry, trigonometry that you learned. Now, if omega is greater than 1, that would mean that the universe is kind of curved in on itself, and it would collapse too quickly for stars to live long enough for life to develop on planets. So here, I think these triangles would look like they're less than 180 degrees. And for omega greater than 1, this is kind of a surface kind of, I don't know, expanded. You take this thing and turn it into a saddle, looks like in this picture. Then these angles are bigger than 180 degrees. And in this case, if omega is less than 1, the universe would expand so quickly that the galaxies couldn't accrete together and stars couldn't form. So omega really has to be close to 1. And we have evidence now that it is almost exactly 1 from observations of the cosmic background radiation. So one of our big question is, what is that dark matter? What is all that stuff out in the galaxy that's making everything have to go faster to stay in orbit? We don't know. Martin Rees thought we might know by 2005. The lab has been trying to find out what it is forever, and other labs have too. Livermore's worked on this. People all over the world have worked on this. And here are the possibilities that he lists. Massive compact halo objects. These would be brown dwarfs, kind of failed stars. They just didn't get massive enough to start burning like our sun. So free-floating planets. So what if you just took Jupiters and flung them out into space? There's not enough of them. Black holes, there's not even enough of them in our galaxy to make that up. We were off looking for matter in neutrinos. These, though, move the speed of light, and they don't work with our cosmological models, and we can't even find enough mass in neutrinos to make up that difference. Weakly interacting massive particles have been sought for decades. They keep doing more and more experiments, and they keep narrowing down the parameter space where these hypothetical particles could exist, but they haven't found any yet to the limits of the detectors that they've looked for. I looked a little bit online about axions today. I really didn't know much about them. They're kind of light, weakly interacting particles. They actually can interact electromagnetically too. And there are lots of experiments going on to look for these. They haven't found them yet, but that is still considered one of the leading candidates. And this latest candidate, primordial black holes here, is maybe getting traction for a number of reasons I can talk about later. Finding black holes that were left over from the beginning, from the formation of the universe. One of the things you have to consider is that black holes will evaporate, and the smaller they are in mass, the faster they evaporate. Right now, the only black holes that could be left from the Big Bang have to be 10 to the 12 kilograms, which sounds like a lot. It's like the size of an asteroid. And they can also go way up high to 100,000 times the mass of the sun. But what we're looking with the James Webb Space Telescope, they're seeing some interesting objects far away. They're called the red dots. And there are some scientists that think that those might be these primordial black holes. So we're also are making gravitational wave detectors, and we're going to be launching them. Well, 2035 now is the latest date. This is earlier when Martin Rees wrote the book, that might actually find gravitational waves from primordial black holes in the early universe. So there's hope we could detect it actually in our lifetime, at least in some of your lifetimes, might be able to see those. And then another possibility is that dark matter really doesn't exist, and the theory of gravity needs to be modified. And there are people working on modified Newtonian dynamics gravity models. We had a student from New Mexico Tech here last month who just got his Ph.D. in that field. But many people, again, scientists don't. This theory explains some things, but it doesn't explain other things. So it's not that popular. It's not catching on yet. But if we never find any dark matter, it might catch on again. Yeah. Okay. And here's the fourth number. This number is another Greek letter, the capital letter lambda there. And lambda is the cosmological constant. You may have heard that this Einstein had come up with this hypothesis or this term in his equations, and then he said that was his biggest mistake. It shouldn't be there. It should be zero. It shouldn't be there. But then, in the late 1990s, just as Martin Rees was finishing off this book, they discovered evidence for an accelerating universe, which means that the cosmological constant is not zero and it's real. So Rees himself wasn't sure that this discovery was going to hold up after he wrote the book, because the evidence was there, but they just had found a few supernova at that point that were actually showing the accelerating universe. But it's held up and it's gotten refined. So we really do think that lambda is a real number now. And it's the cosmological constant which drives the accelerating expansion of the universe and is associated with dark energy. So this was discovered in 1998 by measuring the velocities of distant supernovae that are used as standard candles. So what does that mean? There's certain kind of supernovae, they could be popping off in distant galaxies, but they're all formed in exactly the same way by white dwarf accreting mass or white dwarf merger, and they should all have the same brightness. Again, assuming the laws of physics are the same in these other galaxies, and other things like the composition wasn't too far off from what we see locally. So it's held up pretty well. We think this is real. And the density of dark energy is really something associated with space-time itself. We think it's 0.683 fraction of 1 right now. And we also think that it increases as our universe expands because it's a property of the space-time. So if space gets bigger, the amount of this is also going to get bigger. And it exceeded the matter density around 7.8 billion years ago. So the expansion of the universe has been going on for a while. We think we're 13.8 billion years old now in our galaxy. So it's been going on for 7.8 billion years. And it only competes with gravity at intergalactic scales. We really won't be able to feel this nearby. So this is a little bit of evidence. This is a Hubble diagram for supernovae, and on all these yellow things you can see here are just data from many, many supernovae at different distances away from us. And this is plotted by redshift, and this is just how fast are these galaxies or these supernovae expanding away from us. So a redshift of 1 means you've taken the wavelength of the light and doubled it, and 2 is 4 times. Twice as long of wavelength, so it's redshifting. Things are going to longer and longer wavelength as they go far away. So the blue dotted line would be what would happen if we could find all the missing matter and we had a non-accelerating universe. But as we look further and further back in space, you can see that these galaxies and these supernova are receding faster and faster. So this is our evidence that there is dark energy. This picture and the next one are maybe a little bit hard, but maybe they help you picture what we're getting out of these expanding universe models and cosmological constants. So on the left, well, first of all, there's the present day. These are all flat universes there in the present. And if you try to, on the left, this would be a decelerating universe. This would be if the cosmological constant was actually attracting rather than repelling or causing making the universe come together rather than making it go apart. And that kind of universe would actually not live, wouldn't have, the age today would be much less than the stars we see. So that can rule it out right there. We get maybe a 4 or 5 billion year old universe there on the left. And let's see, this one is a little bit less extreme, but it's still not old enough. The coasting universe, whoops, my husband said that the coasting universe, it really implies there's no matter in the universe either. So that's not right. But it only gets down to about 13 billion years old. I keep touching the wrong buttons, I'm sorry. And on the right is what we think we have, the accelerating universe. So that universe has about the right age. If we extrapolate back, it's 13.8 billion years old, and it's going to expand faster and faster in the future. And just plotting these kinds of things on lines is in this picture right here. So this is that recollapsing universe. When you look back, you're only here at 4.4 billion years for the age of the universe. So that's too short. We see stars old, 13 billion years old. This is the critical universe. And this is what my husband said he had to teach at UNMLA, 15 years ago. They couldn't find the extra missing matter, and they didn't know about the accelerating universe. And all the models were saying that the universe was about 8.8 billion years old. But, we knew from stars that it was a lot more. And this is the coasting universe that couldn't exist because it would have no matter in it. And this is what we think we have, the accelerating universe. So it goes back to almost 14 billion years, and then it's going to accelerate there in the future. Okay, let's see, what do I have here? Okay, so now we're going to bracket these numbers. What if lambda actually were bigger? So this means that the dark energy is higher. There's more dark energy. It's going to be repelling. It's going to be pulling the universe, the fabric of space-time apart, just pulling everything apart. Well, galaxies wouldn't form or they would be disrupted. So that wouldn't be good for our Earth to exist and life to exist. And what if lambda were smaller? We probably wouldn't know, as long as it wasn't negative, attractive and causing the universe to collapse. We may not know, but we could observe, perhaps in billions of years, that we continue to see distant galaxies instead of noticing them accelerate away from us so fast that they would leave our field of view. And this was a new idea to me. We actually think right now we can see out to 46 billion light years away, and our universe is only 13.8 billion years old. How can we see 46 billion years? That's because at 46 billion years, that stuff out there used to be closer, sending stuff to us at the speed of light. So it sent it to us when it was closer and we can see it, but now it's 46 billion light years away, right? And we think that in the future, there's going to be a limit. Anything that is 60 billion years away from us, no matter how long we wait, we're never going to be able to see it. It's always going to be going away from us faster than it ever was close enough to us to send us any light. So I think that's pretty cool. And so if lambda were smaller, it would be even worse. We would start to see, we'd see stuff receding. We'd see nothing after a while. No, actually, we'll see that. If lambda were smaller, we might be able to see further away. So if the lambda bigger, it would be worse. Everything would just recede from us, which I think is really cool. I never knew this before. Okay, so here's the fifth number, which is Q. This number is 1 over 100,000, or 10 to the minus 5 if you want to do exponential notation. And it is the amplitude of primordial density fluctuations in the early universe that had been preserved in the cosmic microwave background radiation. So when Martin Rees wrote the book, they actually had this map on the right from the Cosmic Microwave Background Explorer. This data had just come out, and it looks, this is way exaggerated. What you're supposed to see here is a smooth, this is the whole sky just projected on this stretched out thing in all direction. And you're supposed to see that it is all exactly 2.72 something degrees Kelvin. It's all supposed to be that really cold number, 2 degrees above absolute zero, the whole thing. And we see it the same in every direction, except there are these little fluctuations in it that are only 1 out of 100,000. So the red stuff is a little bit cooler than 2.715 by, 100. You put a bunch of zeros on that fifth decimal, it's a little bit cooler. And then you can, a little bit higher, it's a little 10 to the minus fifth higher in the blue stuff. So these fluctuations are there. So that was preserved. This microwave background was released, I think the number is 380,000 years after the Big Bang. And the reason it got released is that it got cool enough when things were expanding that the electrons and protons combined, and the photons could then not scatter off the electrons, but they could just whip out and get out to us and reach the Earth now at, the age of the universe minus 380,000 years later. So that's what we see. So what would happen if Q were just a little bit larger, or whoops, I got the wrong button again, or 10 to the minus 4, so 1 out of 10,000 instead of 1 out of 10 to the fifth. Well, the regions far bigger than galaxies would then collapse and condense into black holes. So what happens with this cosmic microwave? It's preserving these fluctuations. And wherever there's hotter stuff, it means there's a little bit more matter there. And that becomes the seed of galaxy clusters and superclusters that condense much later in time. So all of this seeded our galaxy formation and our galaxy supercluster formation. If it was all completely flat, it'd be hard to get gravity to pull something together to make a galaxy. But if Q were bigger, big regions would condense and collapse. And we'd make huge black holes. Any stars forming would be too close to each other and to the black hole, so you couldn't get a stable planetary system. On the other hand, if Q were smaller, the universe would be too flat, too smooth. These fluctuations wouldn't be there. The galaxies would be very small. They would take forever to form. Star formation would be inefficient. And with the small galaxies, if they did manage to make a star that made a supernova that could give us some elements that would help make the Earth, the supernova would just have strong winds and blow the material right out of the galaxy because it couldn't hang on to it. So it wouldn't be available for the next generation of stars to form and life to form. So this number really has to be pretty finely tuned to get life. So I'm just trying to give you another analogy here. This is a picture of ripples on the lake in this case. So there you have these ripples on the sea of 2.7 degree radiation in the early universe. So you see how small these ripples are compared to the depth of the lake or the ocean. That's kind of a way to think of these ripples. They're very tiny compared to the 2.7 flat smooth universe. And many scientists have tried to do simulations of galaxy formation. And this is just one I took out of a journal article. So you start by putting in the ingredients to the universe and the kind of 10 to the minus 5 fluctuations in the matter, and then you just run it forward in time. So this is a ways forward in time, and you can see that the galaxy superclusters are condensing, and these bright spots here are galaxies forming. So we can compare what we see in these simulations statistically with what we see from the space telescopes today and try to find out if we put the right ingredients in at the beginning in our models. So these are very useful. One of the things that Martin Rees did not discuss very much, but he also doesn't discuss the weak nuclear force, by the way, very much at all, is the inflationary universe theory. So this is an extra tack on to the Big Bang theory, but it is pretty well accepted actually because it it explains a few things. The Big Bang itself explains why we have the helium abundance we do today. But this helps explain why the universe is so smooth and so homogeneous. In every direction we look, it looks the same. And why we only had those very tiny fluctuations, 10 to the minus 5, 10 to the minus, 10 to the minus 5, in the microwave background. So this idea was put forth in the late 70s. And they say that inflation occurred around 10 to the minus 35 seconds after the Big Bang, so almost immediately. And if you think of it this way, if you had a wrinkled surface and you stretched it by a huge factor, deviations from flatness would become minuscule. So this helps explain why omega equals 1. And it also explains why gravity and expansion, well, omega is 1, gravity and expansion are balanced. And it explains why Q is 1 over 100,000, why that is so small. So this theory has a lot going for it. It explains some stuff about magnetic monopoles, which I'm not going to talk about. I don't really know enough about that to tell you. Take another whole lecture. Okay, so the 6th number. This number is kind of obvious to me. I don't even know if I would include it. It's the number of dimensions of space. It's 3. We live in 3-dimensional space, right? Up, down, right, left, forward, back. And we have one time dimension. I don't know if I consider time a dimension. It only goes forward. It just seems different somehow. I don't know if I would lump it in with as a dimension, but it's considered the 4th dimension. It's time. So what happens if you would change the number of dimensions? So what if you go to 2? Have any of you read the Flatland book? Yeah, a few of you read it. I read it when I was very young. Yeah. It talks about a flat universe, or they have flat beings going around. Well, the problem with 2 dimensions is that complex structures can't form. For example, Martin Rees says you can't cross 2 wires because you have to go into a 3rd dimension to get them to cross. Or say you want a digestive tract, well, you just divide the being in 2 pieces. You can't, snake it around in between stuff. So 2-dimensional life is not very likely, probably impossible. And on the other hand, I thought, well, why not bigger dimensions? What about 20 dimensions? Who cares? You should be able to go as high as you want. Well, he points out that if D equals 4, it has this really bad property. Gravity and electromagnetism, remember I said they were inverse square forces. They drop off as the square of the distance away. If you're in a 4-dimensional universe, it becomes 1 over r cubed. And you go, well, so what? Well, the problem with that is that then planet orbits are unstable. Electron orbits around protons are unstable. You just can't make life unless you change something else too, right? So if this was 4, leaving everything else the same, it's not going to work. Now, they were just starting, well, maybe they've been doing this for a long time, talking about grand unified theories of the forces of nature. And this doesn't really preclude superstring theory, or this other theory that's more of a 2-dimensional string, a brane called brane theory, like membrane. And then these theories, there are 10 or 11 dimensions, and 5 or 6 space dimensions in them are curled up or folded up, so they're invisible to us. So maybe if these unified theories are predicting, there's many dimensions, 10 or 11, depending on which one you pick, but we only can see 3. So we'll see. We can't prove these theories. They've made no testable predictions yet. So who knows if we ever will. Okay, on your table, we have I tried to make a summary that Kirk asked me to make for you of the 6 numbers and what their definitions are and what their values are that we believe they are, and also how low could they get and how high could they get before you couldn't have life anymore in our universe. So out of all of these, Martin Rees doesn't give you any numbers for low and high, for omega or for lambda. But I could find information today, these days on the web about omega that has to be very, very close to 1 right after the Big Bang, because inflation just, made it happen. And also for lambda, it can be as low as an attractive, instead of a repulsive force, 10 times bigger, but in the negative direction, or 10 times larger, 10 times smaller, larger in the negative direction, or larger in the smaller in the other direction. And that comes from a paper by Steven Weinberg, who actually tried to do the calculations for what it would take, where it would have to be for life to exist in our universe. So I'll leave that with you as an example. And I'm going to go on here and tell you about where does that leave us and what does it mean about hypotheses? Maybe I should talk about these questions first. Are these 6 numbers, are they related or connected or constrained by each other? Rees doesn't really discuss that. Why only 6? Are there actually more? Are there less? Could a grand unified theory or this theory of everything explain their values and relate them to each other? And also, what physics do we not know that's operating where we can't access? In the first million years, right, first millisecond after the Big Bang, or even inside black holes. So I'm going to define, Rees's bottom line is that these are really finely tuned for life. So is that just a coincidence, or are there many, many universes and we just happen to be in the one that they're tuned for life? Okay. And this is just a quote from Wikipedia, not from Martin Rees. He says, the anthropic principle suggests that the existence of a multitude of universes, each with different physical laws, could explain the asserted appearance of fine tuning of our own universe for conscious life. And the weak anthropic principle posits that we exist in one of the few universes that support life. So this is my last slide. It's hard to see. It's actually a joke that Martin Rees conveyed in his autobiographical article in the Annual Review of Astronomy and Astrophysics. And he's going through his life and all of the scientists he's met and all the work he's done. And I just took this quote out. It says, some years later, I was on a panel at Stanford University where we were asked by the chairman, Bob Kirshner, on the scale, would you bet your goldfish, your dog, or your life, how confident are you about the multiverse hypothesis? That there's many, and he says he was nearly at the dog level. And Andre Linde, who was on his panel and had spent 25 years promoting the theory of internal inflation, said he'd almost bet his life. And later on being told this, another eminent theorist, Steven Weinberg, said he'd happily bet Martin Rees's dog and Andre Linde's life. So he didn't want to bet those, and he bet other people's on it. So you can see people are not quite certain of this multiverse hypothesis. They're almost willing to bet their life or their dog. And he says at the end here, Andre Linde, my dog, and I will all be dead before this is settled. The concept will remain speculative until physicists can supply a theory that applies under the extreme conditions at the inflationary era, and which has gained credibility by making correct predictions about physics at low energies where it's testable, where we can do experiments. We can't do any experiments on multiverse because we can't access these other universes. They're in other universes. We can't go do experiments to find out what's going on over there. But the multiverse concept is science and not metaphysics, and it may be true. That's how he concludes. Okay, I'm going to stop here and take questions, or we can discuss at the tables. Thank you.
Okay, are there any questions? And we do have a bunch of questions on the discussions later on. Okay.
There's somebody back there. Do you want to take the microphone to them?
Okay. Oh, yes, here we go.
Thanks for a really interesting talk. I wonder if any of the conclusions about the effect of the constants are experimentally verifiable in any way, not just by simulations, but are there any experiments that can show that things are as finely tuned as you suggest?
Well, we certainly have measured the numbers for the dark matter, the dark energy. They were able to do that, assuming the Big Bang, of course, by looking at these even better cosmic microwave background maps that came out after Martin Rees's book. And by looking at these fluctuations, it tells us a lot about how much dark matter, how much dark energy, how much regular matter there is. And that's why we know them to like 3 digits. That's what I was showing you. So that's some data. Which other one? We can measure gravity to electrostatic pretty well. Is that really the question, or are you asking a different question?
No, my question was, I believe the numbers.
Okay.
That it's the best that we have. My question is the implications of the numbers. That, for example, if the fluctuations in the original creation of the universe were different, do we really know that those conclusions are correct?
Yeah, that is
these implications. That's what I was asking.
Right. So it would take someone, some research to do some research in these different numbers and maybe write a journal paper. Say, what if it's different by so much? Then you would try to do galaxy modeling, do planet star modeling to see what would happen. And in some cases, like this Omega Lambda, Steven Weinberg actually did a paper looking at those limits and set them. This number of 10 to the, well, let's see, this 100,000 one, I believe, Martin Rees and Andre Linde, I think, or maybe Max Tegmark, I can't remember. One of the other collaborators actually did a paper constraining those numbers. So in these other cases, I think it would make a really interesting project to try to constrain, how far could you go and not have life as we know it? Yeah, that could be done. My student at the lab is looking at the Big Bang and changing the reactions, saying what if the DT reaction, the deuterium plus tritium reaction, didn't work? What would happen? All right, and it turns out you still make all the helium the same way, as much helium, but just a different route. So you can do experiments, numerical experiments like this, to figure out what would happen. Yeah. But those would make good projects for students, sure. There's somebody here. There's somebody over there too.
Oh,
That's right, go ahead.
Oh.
I think you were both.
let's see, I've been retired since 99, so some of my information might not be current. But some of you remember or know John Middleditch. He led the astrophysics colloquium for a number of years, and he very vociferously claims that dark matter is a huge hoax. And he is, he's a very sharp guy. Now, I don't know if he's changed his mind, but have you had a discussion with him on this, or?
I haven't, not recently.
He gave me one of his papers, which I frankly couldn't understand. But anyway, he's not a timid fellow, right?
Mm-hmm.
And he says it's nothing but a huge hoax, and he's been proclaiming this for years. And I just wonder if you had a comment.
Well, my comment is that we've been looking for the dark matter for years and haven't found it, right? So we haven't found the candidate for the dark matter. What is the dark matter? So he could very well be right.
He has a physical explanation for the observations, I
Right,
think.
that is not dark matter.
But I
Okay.
could not follow his
Right.
reasoning. Okay.
Yeah, if we rule out everything else, we may end up going to other explanations like that to understand the data. Yeah. Any more? There's a question over here. No more questions on this side? There's one over here. Okay.
Yeah, the slide when you had the satellites.
Yes.
Can you go back to that? Because
Okay.
I still don't understand. I want to make sure I heard and understood what you said, which was the satellite on the outer side is going slower.
Right.
And that doesn't make any sense to me.
Yeah.
Looking at that.
Well,
How can it stay geocentric?
it has to be going at just the right
Yeah, and but it's
velocity to stay in orbit.
Yeah.
So gravity is pulling in on it. It's trying to go straight and gravity is pulling in. So it ends up like changing its vector and turning. So it's always turning, always and always turning round and round. Now it's going slower because it's farther from the Earth and the gravity isn't as strong out there. So it doesn't have to go as fast to stay in orbit. Gravity's pulling on it less.
I know you're saying that.
Yeah,
I'm
okay.
sorry. But when I look at that, the distance it's traveling, how does it possibly travel that distance in the same rotation?
It doesn't,
of the Earth?
oh, well, the inside one travels around once every 90 minutes. The
Okay.
outside one travels around once every 24 hours.
Gotcha.
Okay.
That's
Yeah,
the difference.
that's what we needed. That's what was missing on this chart. Okay.
Gotcha.
I'll put that on for the next time. Okay. Yeah. Geosynchronous means it stays over the same point in
Exactly.
the Earth.
Inner one is
So
not.
it's going around once every 24 hours and you get it just about the right distance away. It'll stay over at the same place. Yeah. The inner ones are going around every 90 minutes. Yeah.
Gotcha.
Yeah. Good. Good question. Okay.
Hello. I had a question about the connectedness of each of the parameters there. I kind of naively think that might be pretty straightforward, like a Buckingham pi. It's pretty easy to pin down the relevant parameters if you have a good understanding of your physics. I wondered if you had any comment on.
Well, I think
Yeah.
he never talks about them and whether they're connected. And I think they possibly are, like you said. So maybe we should do the Buckingham Pi thing on it and see what you can
No.
do. Yeah. Maybe I should try to talk to, I don't know, I just learned Buckingham Pi a couple years ago and what that does. It's like a dimensionless analysis that breaks things down into what's the simplest, simplest variables and fewest number of equations to solve the system. So yeah, it would be, I think they could be connected, but yeah, but that was more my question, and he doesn't really discuss it. Yeah.
Well, thank you.
So Joyce, I've seen people play around with some equation, which I don't know, and that's my question, which equation they play around with to get the right amount of dark energy, dark matter, and ordinary matter. What equation is that?
I'm not going to be able to answer that right now.
Join me.
There's an Einstein equation. It's got some terms in it.
Einstein field equation, is that correct? Do you want to?
Maybe one of the other physicists in the room have remembered this.
No, okay.
It has a lambda and a c cubed and the omega, and yeah, it's got a bunch of stuff in it. Yeah. Yep. We can look it up on Wikipedia afterwards. And by the way,
Is that an AI source?
I doing research for this talk, I found the most reliable stuff was Wikipedia. AI would get me kind of close. Sometimes AI would contradict itself or give me the wrong answer to a question, but it could at least send me to some sources. So most of the charts I took out of this are from Wikipedia, Wikimedia Commons, so they're public domain. I could use them by referencing the article. The book itself has almost no pictures in it, so you're not going to see any of this in the book.
Let's see.
Yeah.
I read a book recently by a German guy named Unsinger on AI, and he said there were only two numbers, but I just remember they're not dimensionless. One number is c, speed of light, and the other is Planck's constant. And that was his claim that there are really only two numbers. But
All right. Well, here's a Wikipedia article. Let me find it. There. It said that there are 31 constants in the standard model of particle physics and cosmology combined. And I couldn't even list them all on here because that would take up 5 slides. But some of the ones I thought they were going to talk about were gravitational constant and speed of light. Why is the speed of light what it is? The fine structure constant, which is that 1/137 ratio. I found it really interesting that that almost looked the same as epsilon. They have nothing to do with each other, but it's the same number. Planck's constant, Boltzmann's constant, all things we learned in like our college, at least physics classes, all the masses of the particles. So yeah, there's a lot of numbers that we don't, the grand unified theories are going to have to explain all of these. Yeah. And relate them to the cosmology numbers, the 6 numbers. If they can break it down to 2, that'd be great. Relate them all using Buckingham pi to 2, that'd be great. Yeah.
Do you want to break into table talk now, or are there any more questions?